So we've previously discussed the notion of direct simplicial approximation, and now we want to generalize that. So again, we've got some continuous map P from the realization of simplicial complex K to the realization of L. Yeah, we've discussed what we mean by having a direct simplicial approximation, which would be a simplicial morphism from K to L. But you should realize that it's generally not possible to find a direct simplicial approximation. See, I mean, it's kind of a rather simple case. I mean, K and L could both just be like a single triangle, just the boundary of a triangle, so that's homeomorphic to a circle. And then P could be a map from that circle to itself that wraps around itself 56 times or something. That can be very kind of wiggly. But simplicial maps from that triangle to another triangle, I mean, there are very few of those. They're not flexible at all. So typically, you're not any kind of reasonably complicated continuous map from mod K to mod L is not going to correspond to a simplicial morphism from K to L. But the situation will improve if we can subdivide K. I mean, again, in the case where K and L are just like triangles, then you subdivide K lots of times, then you subdivide it once, then you just get a hexagon. You subdivide it twice, you get a 12-sided polygon. Every time you subdivide twice as many. So you subdivide a few times, you get a polygon with thousands of sides, and then it's very easy to wrap it around a triangle 56 times or more times, whatever you want. So that's what we want to make systematic here. So by a simplicial approximation for P, we mean a pair n, f, where n is a non-negative integer, and f is not a simplicial morphism from K to L anymore, but a simplicial morphism from the nth iterated subdivision Kn to L. And the condition is that it's supposed to be a direct simplicial approximation for the composite P composed with beta n. So let's display the kind of maps we're looking at here. So here was our original P. It's a continuous map from mod K to mod L. And then beta n is a continuous map, a homeomorphism even, from K bracket realization of K bracket n to the realization of K. And so this map P ring B bracket n that we're looking at here, that's that diagonal across there. Got simplicial morphisms as we've got here. So here, remember, beta n itself is not a simplicial, it doesn't come from a morphism of simplicial complexes, but it is at least homotopic to this mu bracket n, which is realization of this mu bracket n being an actual simplicial morphism from K bracket n to K. And then F here is, again, it's a simplicial morphism from K bracket n to L. We look what happens in homology. Okay, so these guys here, these are simplicial morphisms, and every simplicial morphism gives you a corresponding homomorphism of homology groups. So we get mu n star from h star K bracket n to h star K, and f star from h star K bracket n to h star L. But we proved, remember, that this mu bracket n star is actually an isomorphism. So it's legitimate to define a map from the homology of K to the homology of L, which we're calling n, f star. We just do the inverse of this mu n star here, going up there, and then we do the f star. So that's our definition of n, f star. So the key point is that every map, every continuous map P from mod K to mod L has a simplicial approximation. So to prove this, and again, well, if you think back to what we did with covering spaces and covering homotopy theorem and so on, there the idea was that we had some open covers and Lebesgue numbers, and we subdivided things enough so as to make sure that the radius was smaller than the Lebesgue number, and we're going to do the same sort of thing here. So we look at the open stars of the various vertices of L. Okay, remember the open star of B is the set of points where the coefficient of B is strictly positive. And so that's clearly an open set, and every point in the realization of L has a positive coefficient for some vertex, so that proves that the sets O star BL they cover the realization of L. So now we can look at the pre-images those under the map P. So remember, if you've got a continuous map, then the pre-image of any open set's open. So the pre-images of these sets O star BL, they're open subsets of the realization of K. And because the open stars cover mod L, the pre-images are going to cover mod K. And now mod K, that's a compact metric space. So every open cover has a Lebesgue number. So we can have a Lebesgue number epsilon, so that any set of diameter less than epsilon is going to be contained in one of the sets of the cover. So now if you think about the usual kind of affine embedding of mod K, where we just send K, the ith vertex to the ith basis vector, as we mentioned previously, that has mesh 2. And so if we compose that with beta to the I, then we're going to get embedding of mod K to the I in Euclidean space, where the mesh is at most 2 times d over d plus 1 to the power I by the proposition we proved on the reduction of the mesh. Yeah, here, that's where d is the dimension of K, remember. Yeah. So, but this d over d plus 1, that's less than 1, so the powers of d over d plus 1, they converge to 0. So if we choose n to be large enough, then twice d over d plus 1 to the power n will be less than epsilon. So we choose such an n. Now let's think about any vertex A of this n-fold subdivided copy of K. So if we look at the ball of radius epsilon around this point, around the point beta Na, so that's going to be a subset of the realization of K, of radius less than epsilon, of radius precisely epsilon, and so that's going to be contained in the pre-image of the open star of pre-image of one of these open stars. It's got to be, in other words, it's got to be contained in one of our sets of our cover. And now let's think about any point X that lies in the open star of A in the subdivided complex Kn. So any such point X lies in a common simplex with A, and so the distance from the beta nx to beta na, that's going to be less than or equal to a mesh of beta n, which is less than epsilon. So that means that this point beta the nx lies in this ball b beta na epsilon, and so it lies in the pre-image of this open star. So that means that if we look at this beta nx, it lies in the pre-image of the open star of Fa, or in other words, that P of beta nx lies in the open star of Fa. That works for any point x here lying in the open star of A. So we find that P composed with beta n applied to the open star of A and Kn is contained in the open star of Fa and L. So remember, we said that for any vertex A, we can choose some vertex Fa and L which has this property. Okay. And so we do that for every A, and then that gives us a direct simplicial approximation for P composed with beta n. And that by definition means that F is a simplicial approximation to P. Okay, so that proves that for any P we can choose a simplicial approximation, and then say we can choose a simplicial approximation n, f star, and then as we said before, that gives us a map of homology groups n, f lower star from the homology of K to the homology of L. But the point is, the simplicial approximation is not unique. There's plenty of choice about how we do the simplicial approximation, and so we might get two different homomorphisms from H star K to H star L apparently, but in fact we don't. The point about this proposition is that any two different choices of the simplicial approximation will still give us the same homomorphism of homology groups. And so because of that, we can just define P lower star to be n, f lower star for any possible choice of simplicial approximation n, f, because if we chose a different one, it would still give the same answer for p lower star. So to prove that, well, so we've got these two different simplicial approximations, and by swapping them around if necessary, you can assume that n is less than or equal to m. So saying that n comma f is a simplicial approximation, so that means that f is a map from Kn to L, which is a direct simplicial approximation for p composed with b to n. And now remember, m is bigger than n, so we've got a iterated mu map from k to the m to k to the n, and by what we proved before, that's actually a direct simplicial approximation for the power of beta to the m minus n, going from the realization of km to realization kn. Okay. And we proved earlier that direct simplicial approximations are kind of compatible with composition, so we can just say that this f composed with mu m minus n is a direct simplicial approximation for this p composed with beta to the n composed with beta to the m minus n, and then these betas cancel out. That's just p composed with beta to the m. On the other hand, mg was supposed to be a simplicial approximation, so that means that g is a direct simplicial approximation for p composed with beta to the m. And we proved earlier that if you've got direct simplicial approximations for the same map, two of them, then they're going to have the same effect in homology. That's proposition 19.10c. So we see that f lower star composed with mu star to the m minus n is the same as g lower star. Now remember, this nf lower star so we have to take this f lower star and compose with the inverse of mu to the m star, mu to the n star, whereas this guy is g star composed with mu to the m star inverse. And so just by taking this and composing with the inverse of mu star m, we're going to get that these two things are the same.